Okay, in this video we'll learn how to solve ordinary differential equations using power series centered at zero. In other words, what we'd like to find is a solution in the form y is a sum of Cn x power n from 0 to infinity. Now, since you are dealing most of the time with first and second order differential equations, you need to find y prime. It will be a power series Cn n x power n minus 1 that could start at 1 infinity, and y second will be a sum of Cn n n minus 1 x power n minus 2 from 2 to infinity. And we will apply this to differential equations where 0 is not a singular point. So let's see an example. We need to find two power series solutions of the following differential equation: x minus 1 y second plus x squared y equals 0. The first step here is just to expand. We obtain x y second minus y second plus x squared y. It has to be 0. The second step will be to replace y second here with the power series. So that means we'll have x times the sum of Cn and n minus 1 x power n minus 2 from 2 to infinity. Then minus the same thing, sum of Cn and n minus 1 x power n minus 2 from 2 to infinity, plus x squared sum of Cn x power n from 0 to infinity. Now we need to combine this power series. For that, first we need to multiply with all the times having x, or we can just in general just multiply with any coefficients inside the power series. So for this first power series, we obtain a sum from 2 to infinity Cn n n minus 1. Now we obtain x power n minus 2 plus 1, that means n minus 1. Minus the second will not change, Cn n n minus 1 x power n minus 2 from 2 to infinity. And the last one plus sum, it becomes Cn x power n plus 2 from 0 to infinity. And this has to be 0. Okay, now from here we need to do some substitutions to obtain the same exponent and later on to obtain the same starting index. So the first one, we just have to replace k with n minus 1. Okay, k is n minus 1, which means n is k plus 1. We could change the name, but actually at the end it will be still the same power series because the n or the k here are just indices for describing the power series. So we can just keep the same name. Here k will be n minus 2 because the exponent we have here is n minus 2, which means n will be k plus 2. The last power series k will be n plus 2, which means n is k minus 2. Now, if we do these substitutions, here everything should be changed in terms of k. When n is 2, k will be 2 minus 1. That means we have a power series starting at 1, infinity. C, n is k plus 1. We have k plus 1. A, n is k plus 1. K minus 1 will be k, x power k. For the second power series, when n is 2, k will be 0. So we start at 0 to infinity. C, k plus 2. K plus 2 times k plus 1 x power k, and the last one, sum of n will be ck minus 2 x power k, where k now starts at, when n is 0, k will be 2. this has to be 0. Now we have three power series with the same exponent, which is k, but different starting indices. So we need to have a common starting index, which will be the highest among these three, that means 2. So from the first power series, I need to replace k with 1. When k is 1, we obtain, this is 2c2. Then the remaining power series will be starting at 2. For the second, when k equals to 0, we obtain 2c2. So sorry, this is when c2, when k equals to 1, we obtain 2c2x minus, for this power series, when k equals to 0, we obtain 2c2 minus 2c2, and then minus, when k equals to 1, that will be 3 times 2, that means minus 6c3x. And now the remaining power series are all starting at 2 infinity. We can factorize ck plus 1, k plus 1 times k minus ck plus 2, k plus 2, k plus 1, and plus ck minus 2, the whole times xk, which has to be 0. Now, before equating to 0, we need to combine the similar terms. The only constant term here is minus 2c2, so we have to have it aside. In terms of x, we have plus 2c2 minus 6c3 times x, and then plus this power series starting at 2 to infinity, ck plus 1, k plus 1 times k minus ck plus 2, k plus 2, k plus 1, plus ck minus 2 times xk, which has to be 0. Okay, now if the power series is 0, that means all terms should be 0. So the constant term must be 0, which means minus 2c2 is 0. The coefficient of x should be 0. It means 2c2 minus 6c3. And the coefficient of xk, which is ck plus 1, k plus 1, k minus ck plus 2, k plus 2, k plus 1, and plus ck minus 2 should be 0 for k starting at 2. These are the relations that we obtain. So from here we obtain that C2 is 0, C3 is 0. Now in this recurrence relation, we need to obtain the coefficient, the constant with the highest index in terms of the others. So here we have to express ck plus 2 in terms of the other coefficients. So ck plus 2 will be ck plus 1, k plus 1 times k, plus ck minus 2 over k plus 2, k plus 1, which is valid from k equals to 2. Now we already have C2, C3. The next will be when k equals to 2, which will give us C4. Now C4 means I place k with 2, that means 3 times 2, 6 C3 plus C naught over, when k equals to 2, we have 4 times 3, that means 12. But C3 is 0 from the previous equation, so we obtain that C naught, C4 is C naught over 12. When k equals to 3, we should obtain C5. C5, we obtain here 3 plus 1, 4 times 3, that means 12 C4. Then plus C1 over, when k equals to 3, we obtain 20, which is 12 C4 will be C0 plus C1 over 20. You can continue the process. When k equals to 4, we obtain C6. C6, k equals to 4, that means 20 C5 plus k is 2, so we obtain C2. K is 4, so we obtain 4 minus 2, which is 2, over k equals to 4, that means we obtain 30. Now C2 is 0, C5 is C0 plus C1 over 20, so if you multiply with 20, it will be just C0 plus C1. So at the end we have C0 plus C1 over 30. Now, when to stop? To know that we may need to go back to the function, to initial function y as the sum of Cn xn, replace Ck, all the coefficients with their values, and see what we obtain. If we need more, then we may need to come back and continue the process. Now, we started with y is C0 plus C1x plus C2 x squared, C3 x cubed, etc. So C0, we keep it as it is, C1x, C2 was 0, C3 0, C4 was C0 over 12, so x4, C5 is C0 plus C1 over 20 x5, and for C6, C0 plus C1 over 30 x6, and so on. Now we need two power series solution of this ODE, so we just need to factorize with C0. The first term will be 1, the next term will be 1 over 12 x4, the third one will be 1 over 20 x5, and here we have 1 over 30 x6, etc., plus C1. The first term will be x, next term will be 1 over 20 x5, and we'll have here 1 over 30 x6. Now, the rule that we will consider in this course is that we just need to get at least 3 times for each power series. 3 times for C0, 3 times with C1, then that should be enough. So this is Y1, one power series solution, and here it should be Y2, another power series solution. If we did not get enough terms here, then we need to go back to the recurrence relation and replace k with 5, 6, 7, and so on until we obtain 3 terms for each of the coefficients.